Good evening guys, welcome to Begins Online Academy Tutorial. Thanks for watching our videos online. Please don't subscribe, please go ahead and press the subscribe button and notification bell. That's our update on this YouTube channel. Thank you and God bless you. Amen. Today we'll be considering what? A topic under physics known as what? Known as the physical quantity. Physical quantity. Physical quantity. Now we're talking about physical quantity. What do you mean by physical quantity? Physical quantity can be defined as any measurable property of a what? Of a substance. Any measurable property of a substance is referred to as what? Physical quantity. And knowing fully well that physics has to do with the study of the fundamental aspect of a universe. And that what? Study of the fundamental aspect of the universe, how the universe works. We need to take into consideration the physical quantity of any object in a world universe. For instance, now if I'm taking myself as an object under physics, now what are the things that are measurable in me as a subject, as an object? For instance, now if I'm considering myself as a body or object in the world physics, and I was asked to take some physical quantity of myself as a body, the first thing that can be measured in me is my temperature, my height, my weight as a person. So these are referred to as physical quantity. My height, my temperature, my blood pressure, they are referred to as what? Physical quantity, because they are the measurable property that I have as a human being or as an object. So any measurable property of an object or body is what we call physical quantity. Now, physical quantity are then specified or identified by what we call units, or what we call units. Now I told you that what? Any measurable property of an element or of a substance is what we call physical quantity. And we said that for physical quantity are specified in units. They are specified in units. For instance, now if I want to measure temperature of my body, I can actually measure it in Kelvin. Now, if I have 20 degrees Celsius, it means that I'm having a body temperature of 20 degrees Celsius. If I say 20, ordinary 20, you won't know what I'm referring to. You won't know which quantity I'm referring to if I say ordinary 20. But immediately I say 20 degrees Celsius, you know I'm talking about temperature. Immediately I say 20 meters, you know I'm talking about length. So physical quantity are usually specified and identified by their units. If I want to measure what? The mass of a particular object now, I must specify whether it is in gram, kilogram, or tons. So units give a particular quantity specification. So, and that's that about what units. So physical quantity are specified in units. And basically there are two major classification of physical quantity based on their on a dependent. Now, what am I trying to say is that there are two major group of physical quantity. There are two major group of physical quantity, which are what? The fundamental physical quantity. The fundamental physical quantity. And what? And the derived quantity. The derived quantities. Or the derived physical quantities. So we have the fundamental quantities and the what? And the derived quantities. Now these are the two major physical quantity can be classified into fundamental and derived quantity. Now let's quickly look at what? Fundamental quantities and units. Fundamental quantity and what? Units. Now when I'm talking about fundamental quantity are the what? These are the what? Quantity that are independent. These are the quantities that are independent. They are the basic what? They are the quantities that are primary. They are very, very primary. They didn't depend on other for the derivation. So they are very fundamental in nature. They didn't depend on others for the derivation. And we have same fundamental quantity in physics. Same fundamental quantity in physics, which I give an acronym of MELTA. Now let's quickly draw this one out because of our time. Now let's quickly write it out. We have the serial number, we have the physical quantity itself, which is under fundamental, the fundamental physical quantity, the unit and the unit symbol, Now, I said we have 1 to 7 fundamental quantity, 1, 2, 3, 4, 5, 6, 7, 8. So we have what? 7 fundamental what? Quantity. Now we have the what? The quantity itself. We have the quantity itself. We have the what? The unit. And the what? And the unit symbol. And the unit what? I call it unit symbol. Okay, we have the what? The quantity, the unit, and the unit symbol. And this type of unit we are talking about here is XI unit, the systemic international what? Unit. The systemic international unit is what we call SI unit, International System of Unit in English translation. So, this system of units, or this system international unit, are the acceptable units in physics. Now, I said that the SI unit are the acceptable what? Units in physics. For instance, now, if we are considering what? Mass as a quantity, as one of the fundamental quantity, mass is one of the fundamental quantity. It has a SI unit of kilogram, but it can also be measured in other units. But the standard of measurement of mass in physics is kilogram. Even though it can be measured in gram, it can be measured in tons, it can be measured in what? In another form. But the SI unit is what? Kilogram. So what am I trying to say is that the quantity of the number of quantity under fundamental are given an acronym melters. I give them acronym what? Melters. So this is mass. This is what? Electric current. This is time. This is temperature. This is amount of substance. This amount of substance. This is length. And this is another level, which is known as luminous intensity. So luminous intensity. So we have the mass, the electric current, which is theory, the time, the temperature, the amount of substance, the length, and luminous intensity. I give it what? The acronym melter, so that it can easily be recorded for. Now we have what? The mass. The SI unit for mass is what? Kilogram. It's very, very important. It's kilogram. SI unit of what? Mass is kilogram. And the symbol for what? It is kg. We have the electric current, which is ampere. The symbol is capital letter. We have the time, which is what? The seconds, which is denoted with small letter x. We have the SI unit of this is Kelvin. Even though we have degrees Celsius and degrees Celsius, degree Fahrenheit, and so on and so forth. But the SI unit is what? Kelvin, capital letter K. We have the amount of substance. We have mole. It is MOL. So we have the length, known as what? The length, the SI unit of length is meter. Even though we can measure it in centimeter, millimeter, miles, and so on and so forth. But the SI unit is what? Meter, which is M. And the luminous intensity is measured in candela, CD. So that's that about the fundamental quantities. These are the fundamental quantities that we have. These are the fundamental quantities that we have. Now moving from here now, we could see that out of this fundamental quantity, there are 3 out of this fundamental quantity that are called basic fundamental quantity. Now, even though these are fundamental quantity, they are the what? They are independent, but there are some out of this 7 that are very basic, like mass, length, and time are referred to as basic fundamental quantity, because it is this quantity that virtually all other derived quantity depends on. It is this 3 major quantity that most of derived quantity depends on for the derivation. So they are called basic fundamental quantity. They are called basic fundamental quantity. Please take note of that. And another thing that we need to consider before we move to the fundamental quantity is that these are the basic fundamental quantity, where we have 7 fundamental, and mass, length, and time are referred to as basic fundamental quantity. So now let's move to the derived quantities and units. Now, when I'm talking about the derived quantity and unit, the derived quantity and units has to do with what? Quantities that are dependent. They depend on fundamental quantity for the derivation. Derived quantities, from your derive, they are quantity or group of quantities that depends on fundamental quantity for their derivations. We have several examples of derived quantities. Have example of derived quantities starting from area, volume, density, pressure, and so on and so on. There are several, but the most important is that they depend on fundamental quantity. Now, for instance, let's consider some few of it. We have serial number, we have the quantity itself, the formula, how they come from the derived quantity, and the unit. So how do we go about that? We have for the serial number, we have the quantity, we have the quantity, we have the formula for the quantity, or the expressions. Then we have the units. Now, how do we go? Number one, let's talk about area. Now look at this. Area itself is length times breadth. That is the formula for calculating area. Meaning that length and breadth are measured in meter. So it will be meter times meter. So the units will definitely be meter squared. You can see it depends on length. Both of them, they are length, they are measurement of the side of an object. So length and breadth belongs to the category called length, and they are measured in meters. So you can see this area depends on the fundamental quantity called length. So that's why it is derived quantity. Now, number 2 is we have the volume as well. Volume known as V. We have length times breadth. Length times breadth times height. This volume is length times breadth times height, which is meter. Length measured in meter. The SI unit of length is meter. The SI unit of breadth is also meter. The SI unit of height is also meter. So we have meter cube. That's the unit. Meter cube. Now we also have, this is very, very important, because they might ask you what is the XI unit, what is the unit of these derived quantities. In fact, it's one of the questions that Jamb usually asks every year. So the next one is when you have another one, we have the pressure, the speed, and the likes like that. We have the speed, which is distance all over time. Distance is also meter, which is meter all over seconds, because the unit of time, so it's same as meter per seconds. Meter all over time, so meter per seconds. I want to show you some things here. We have the velocity and what? And velocity and speed, they have the same what? They have the same units, but the only difference between velocity and speed is because, let me just deal with this, the difference now. The velocity is a vector quantity, while speed is a what? Is a scalar quantity. So this one just have to do with displacement. That this distance traveling in a specified direction over time taking. So they are both having what? Meter over what? Because displacement is measured in meter and time is measured in what? In seconds. So they are both having meter per second. So don't get confused. Speed and what? They have the same units, but the one is scalar, the other one is what? Vector. So now let's just move to acceleration. Acceleration, we are fine. Acceleration has to do with what? Acceleration has to do with what? The velocity all over what? All over time. Velocity over time. Change in velocity all over time. Change in velocity all over time. So meaning that it is velocity over time. So now the velocity itself as meter per second. Please note that the velocity itself as meter per second as its unit, and all over another time. Please, it's very, very important. So meter per second is the velocity, one time is seconds. So when it comes, so it's having power of 1 as well. When it comes up, law of this is that it will become -1. So this one will now become -1. It will now be what? Meter per second squared. So that's how we get the unit of what? The unit of acceleration. So I will stop where, this is where I'm going to stop, where we are going to have force and then pressure, because I want to combine this and this together. We have what? We have force. Force has to do with what? Force is equal to mass times what? Acceleration. Mass times acceleration. Don't forget that the unit of what? Of mass. The unit of mass is kilogram. Have I mentioned it here? Yes, the unit of mass is what? The unit of mass is kilogram. So kilogram multiplied by the acceleration now, which is meter per what? Seconds. This is where I'm going. This is meter per second squared. So the SI unit of what? Of mass is what? Is the SI unit of mass is kilogram. The SI unit of acceleration is what? Meter per second squared. So the unit itself will give you what? The unit itself will give you what? Kilogram meter per second squared. Kilogram meter per second squared. Now, instead of them writing kilogram meter per second squared, kilogram meter per second squared, they give it a what? A single unit. Instead of writing this in a split form, and that unit is what? Called Newton. Capital letter N, Newton. So they meant the same thing. Newton is the same as kilogram meter per second squared. You don't usually find this one easily. It's usually this one that they what? You usually see as force. But the SI unit in a split form is kilogram meter per second squared. So that's that I want to tell us, that we can proceed from here to do what? You can try that of pressure. The pressure itself, the most important is that if you know the formula, pressure is force. Pressure itself is force over what? Area. And since you know the force over area, just come here, put the what? The unit of what? Put the unit of force into what? Into actions. Put the unit of force into action all over the unit of what? Area. And then you arrive at your what? At your SI unit, or unit for what? For pressure. So let me know the words you get in the comment section below. So that's that about derived quantities and its units. Derived quantity and its what? Unit. Now, a factor of what? Of 10 used to express relatively large or relatively large or small units of measurement. measurement. For instance, now let me just take for e.g. now if I have 10,000 meter, instead of me writing 10,000 meter, I can express it as what? 10 times 10 raised to the power 3 meter. And this 10 raised to the power 3, it has a standard prefix, which is 10 raised to the power 3 is kilo. 10 raised to the power 3 is kilo. 10 raised to the power 3 is kilo. This is the same thing as what? Kilo, capital letter K. So if this 10 raised to the power 3 is what? Kilo, definitely I can say therefore this is going to be 10 kilometer. Please, you know that this 10 raised to the power 3 is the same thing as kilo. So instead of me putting 10 raised to the power 3, I will now substitute it with K. So I now have kilometer. So this 10 raised to the power 3 here represents K. So K is a standard of prefix. This K, which is kilo, K, which is kilo, is a standard prefix. So we have a lot of these words. Is a prefix, is a standard prefix. So we have a lot of these prefixes in what? In physics, like gigahertz. We have what? Tera, megabyte, kilobyte, and so on and so forth. Now, let's quickly go into the summary of this so that we don't waste much of our time. We have prefix. The prefix itself, the value of the prefix, the symbol. Now, I would like to just put, you know that this is key already, so I have to extend it to this place that contain everything because we have a lot of them. So now, so we have so now the first one on the list here is the what? Is the we started from the what? From 10 raised to the power 18, which we know as what? Which is known as, we have what? The first one is, let's have it, we have the exa. The exa, we call it the exa. The exa is the value of exa. We have the prefix itself, the symbol of the prefix, the value. The exa is 10 raised to the power what? That is your 10 raised, the value is, the symbol is capital letter E, and the value is 10 raised to the power what? 18. It's not that 10 raised to the power 18, 10 raised to the power 18. The next one is the exa is 10 raised to the power 18. For example, now you want to write example is hexameter, that is EM. You want to use this one now, you can use it e.g. you can have hexameter 10 raised to the power, just like when we have kilometer, you can have hexameter when it is 10 raised to the power 18. You also get to know it when we are using the calculation. Hexameter, we have the pelta is capital letter P, 10 raised to the power 15, difference of 3. So we have the next one is the tera. This is very, very common, the terabyte. If you have a hard disk, you have in form of terabyte, 10 raised to the power 12. We have the words also in form of gigabyte, giga, capital letter G, 10 raised to the power 9. We have mega, capital letter M, 10 raised to the power 6. Then we have the common one, the kilo, K, 10 raised to the power 3. Please note it. We have the words, the hecto. This one is not that common. Hectoliter, or is small letter H, 10 raised to the power 2. We have also the deca, that is DA, 10 raised to the power 1. 10 raised to the power 0 does not have anything, so we move to what? I'll have to continue here. The prefix, the symbol, and what? And the value for the negative ones. For the negative ones, we have Number 8, let's just say this real number. Number 8 here. Now, number 9 rather, number 9. We have number 9. The first part of the negative side is what we call the dead C. The dead C. The dead C. The symbol is ordinary D. We have decimeter. Don't forget decimeter. That is 10 raised to the power minus 1. We have 10, we have the centi. Okay. Before we have 10 centi C, we have 10 raised to the power minus 2. Then we have the millimeter. We have small letter M, 10 raised to the power minus 3. We have the micro. This is very used in capacitance. Microfarad. They usually use it in capacitance very well. They can also use another words, but usually common expressing words in capacitor. So microfarad, which is micro, 10 raised to the power minus 6. Another one that we have is also the what? The nano. The nano, so that I 10 raised to the power minus 9. The next one is the pico. The pico is 12 P 10 raised to the power minus 12. The next one is the femto. The femto, FM, 10 raised to the power minus 15. And the last one, which is the attoseconds. They have 10 raised to the power minus 8. These are very, very important. Very important atto. So these are the standard words, prefixes in what? In physics. So that you know how to convert. Whenever you are given giga, like you are given what? 2 gigahertz. You are not to use this 2 gigahertz like that. What you need to do is first convert it back to normal. You have 2 times. What's your giga? Giga is 10 raised to the power what? 9 hertz. So it is 10 raised to the power 9. 2 times 10 raised to the power 9 that we now use. You are not expected to use 2 in your subsequent calculation. Maybe you have to calculate the velocity of a light or the velocity of a wave. So you have to first convert this 2 gigahertz to normal hertz, which is 2 times 10 raised to the power 9, because giga is 10 raised to the power 9. So please know that, because it helps you to be able to use your units and your data effectively without making a mistake. That's why I'm giving you these introductions, because when we're going to calculations and you are meeting with this, you are meeting with nano, micro, you must be able to know what micro represents. 10 raised to the power minus 6. So that's that about that.